This John Black Superchemist, Polarizers, Fundamentals, and the three polarizer paradox. I want you to ask these physicists, right? How do they, because they tell you that they have quantum entangled photons, how do they prove that they are quantum entangled when it's impossible to test to see if they are entangled? I mean, even if you pass, because they're saying that they'd have to pass or fail both of them, and every degree of, that you can put your polarizer at. Well, okay, so let's say you do 0 degree, 1, 2, 3, and they pass through 0 through 89 degrees. So 89 times they both go through the filter. But what about on degree 90? Both photons are going to be dead. They're going to be absorbed, right? And you still have 91 degree to up to 180 degrees that you haven't done, you haven't checked. So my question is, and that you should be asking them, is how do they know that it's an entangled photon? Because the real answer, the reason that they know, is they're using their feelings and their feelings alone. That's it. It's based on nothing but feelings. And even if the photons both pass through, they put them through degree 0 all the way up to 180, but they saved the 90 degree for last, right? This proves nothing. Even if they all pass through, because each time you put the photons through another polarizer, the probability is reset. Just like flipping a quarter. You can flip a quarter for 1,000 times to get tails. You still have a 50-50 chance of flipping that coin individually. The group, yeah, you can say, oh, he has a better chance of, getting a heads because he got 1,000 tails. Yeah, but that's when you're taking the group as a group. But as you're individually flipping thing, you got a 50-50 shot every time, okay? And it's the same way on here, man. Why is the probability reset each time? Because this and this are reset each time. Because when you they make sure that the the photons are vertical, or they're in the same plane or whatever, right? The oscillation of the E field. But what about where the oscillation is at? Like, in other words, they're all vertical, they're coming down to this polarizer, right? Well, some are going to hit, they're going to be in their oscillation. Some are going to be in their oscillation here, some are going to be here, some here, some here, some here, some here. Some are going to hit this polarizer when their crest is at, at the crest. Some at the midpoint, some where it's at the trough. You have them in the same plane, but you don't have them oscillating the same direction, the same time, same with their B fields. So you have reset it, because you're not going to, if you were going to put them in at the same, so they all hit the polarizer and they all had their crest, well, when they hit it, then yeah, now we're talking about a different story, okay? But you ain't doing that, okay? The angle differential between the polarizer, right, and the photon's E field of oscillation determines the amount of energy or force or torque given to the polarizer's E and B fields. Meaning over here, you got 1 degree difference, 45, 89 degree difference, right? This determines how, because you can't induce in the horizontal, so you can only jiggle in the vertical, and so only your vertical force or energy or whatever can get translated from the photons down to the polarizer, right? None of the horizontal can be translated. Just like when you're inducing a current in the horizontal, none of the vertical can be used. That's why if you're at 89 degrees, you still can't induce a current horizontally in the polarizer, because you have 1 degree of it in the vertical, and that does not translate. You need all of it. You need at least what you get in the 90 degree to induce in the horizontal. You can see right here, this is the most vertical. This is the in between. This is the worst vertical for the E field, right? So if it's most vertical, it can translate more energy to the jiggle, right? So you get more torque. You get here. You can see the B and E fields get smaller and smaller the less you are in the vertical and more you are in the horizontal. So you get less. You have the least vertical amount of energy or force or whatever, torque to transfer over to the photon. Because look at the EV. This is the polarizer, look at this induced, this big one, this is a little less. This one barely induced anything at all. Look at that. Then once they get through into the polarizer, now we got the B field got to be taken care of, right? The B field determines how good the two B fields react with torque. The E field determines how big the fields are. Now we're going to determine how they react. Determines useful torque. This determines torque, the E field. The B field determines useful torque. I wanted to bring this up too because just to clarify, the E field is solely responsible for the magnitude of the E field in the polarizer, right? And therefore, the magnitude of the B field, and etc. So that means the magnitude of the torque also, okay? But it doesn't have full control of the torque, okay? Because the second part of that was that the B field determines the useful torque, okay, when it comes to this. Both, but I want you to understand, I keep saying the B field, the B field, the B field, right? It's really both fields, okay? It's the B field and the E field. They're both equally, whatever, contributing to the torque. But only one, the E field, is contributing to the magnitude that is induced in the polarizer, right? You know, once that happens, then these two come into play on torque. You know what I mean? Because it depends on where they're at in their oscillation. Like up here, you can see this would be the photon coming in, right? But look at the blue dot. You know, these lines don't represent what's going on. The blue dot represents, you know, these are just energy particles or energy whatever. They oscillate back and forth. They don't occupy this entire line the whole time. They oscillate. So when the B field is here on the photon, you can see how it's close to the B field on the polarizer compared to this one. This one's further away. You don't get as much torque, obviously. Red one, you know, the E field, it's oscillating too, you know what I'm saying? And it hit its position in the oscillation. It's basically two vectors. Like I'm saying it's the B field, but it's really a vector, okay, a combined vector of the E field and the B field, okay? And that combined vector determines the torque, the amount of torque, and the direction. I just choose the B field because the whole time we're talking about the E field, that way we can separate, you know what I mean? But I want you to understand, it's both, when it comes to that end part, you know, right here, where, you know, that both fields, it's not just the B field, it's both, you got to take into account both fields. This is the probability wave, okay, which is just a graph, it's not an actual thing, right? You can see the amplitude is red, you know what I mean? And you can square it and you get your intensity, you know, cosine theta squared, right? I want you, and it does represent probabilities, I'm not saying it doesn't. But I want you to understand what this really represents. It represents the distance between these fields, okay? The pseudo vector, or whatever you call it, where it's the combined vectors of both of these E fields and B fields between these two whatevers here, yeah, that's, you know, when it oscillates up here, guess what? The distance is big, and he's right here on the sine wave. When it oscillates on this side, oh, guess what? He's as close as he can be. That's where he is on this. That's what this. I mean, when it comes down to the core, more, you know, thing of it, that's what it represents. It represents distance, okay? And that distance is just, you know, it's proportional to the energy. It's proportional to the force. It's it's proportional to all the crap, man. You know what I'm saying? But when it comes down to the core of it, that's what it really represents, right? And you know, that's why that's why your probabilities oscillate, because this oscillates, and your probability is based on how far away are these two vectors, or these two fields. Well, how far away are they? Because if they're too far, they're not gonna work. They're not gonna give you torque. But you can say this represents the torque. You can say it represents the energy, the force, whatever. They're all the same. I mean, proportionally. Here's your three examples, right? These are the photons. They're all at 45 degrees, or whatever that angle is. So they all induce the same size B field and E field inside the polarizer. But what's the difference? Well, here's the same three people, right? The same three photons, right? Same polarizer. Look, these lines don't represent the E field and the B field. They're just lines. They're symbols. The B field and the E field is an energy particle, or an energy, whatever you want to call it. It oscillates back and forth, okay? See right here, I have the blue dot here. That's where the E field oscillation is at. The rest of the blue line doesn't exist. It's just a symbol, a mathematical construct that we put on paper. It doesn't exist though, right? Oh, this is a path. You know, as it oscillates, it's going to go this way. Now look at where the dot is. And it's going to go even more. Now the dot's here. Here, it depends on when your photon hit the polarizer with its B field. Is this B field here, here, or here? Because if it's here, you can see that here to the B field down here it's a long distance away. This is a bigger distance than this is. You can plainly see this is bigger, right? These two are far away. So obviously you're not going to get as much torque here, right, as you get here, because they're far away here. And we have not even brought up these two things that I'm not even going to bring up yet. But the direction of the photon's B field particle, you know, how it oscillates back and forth, the direction in its oscillation also determines torque, probably, right? Like when I showed the example, I had the two magnets on top of each other, right? And I flipped over the one magnet. Now it started rotating in a different way. Instead of clockwise, it rotated in a counterclockwise. Okay? So this is going to affect it too, right? And I didn't even bring that up. And the direction and the position of the polarizer's B field oscillation also determines torque, right? Because this B field is going back and forth too, right? Now look at this. What if it's here? Or what if it's right in the middle? And you can get through being in the middle, right? But now you take this into consideration, right? Now this is oscillating back and forth. Now this is over here. It might not be able to let that in because it's further away than when it oscillates over here. Now it's close. See what I'm saying? So we didn't even bring that up, which also basically does the same thing what I'm saying right here. You know what I mean? It just adds to it. And this is why our percentage probabilities, they only show us 3 because they don't want us to see. Look, here's the percentages of probability for 15 degrees. This is for 22.5 degrees. Why would our percentage probabilities be uniform like this 175%, 50%? Why would it be like that when all 4 fields, you know, the B and the E field and the photon and in the polarizer, that's 4 fields, they determine everything. All the fields that determine everything oscillate. So I mean, logic would dictate that the percentage probabilities would also oscillate, okay? The only thing that dictates that the probabilities should be uniform like this is magic, feelings, emotions, because showing 3 data points like this when you have 180, you can see right here I have like 9 data points, and you can clearly see it's oscillating. It's not even like you needed all 180, you know what I mean? Same here, there's only like 13 data points. You can obviously see it's oscillating. Why does someone who has PhDs not understand, you know, why don't they admit the polarizer rotates the photon, okay? It rotates it, not only that, it rotates a percentage of all the degrees of difference, you know. All these people, the only one that doesn't is 90 degrees right here. 90 degrees. That's the only, it doesn't get any percentage from that. And that they rotate them so that they're vertical when they come out, right? You get 50% comes out, but 100% of them are in this configuration. So they're saying that basically only the vertical comes through. Well, if only the vertical comes in, that would be 1 over 180 because there's 180 degrees of freedom. But we all know it's 1 over 2, 1/2. Why can't they just admit it rotates the light? When you put that middle filter in, you are screwing with the light. That's why you're changing it. That's why it goes through the 3rd filter. Alright, all we have to go over is the Fresnel-Arago laws for polarized light, and we'll get to that in the next video.